Okay. Who has seen the notes? Thumbs up or digital thumbs up or regular thumbs up? Hopefully you had a chance to at least look at these. If you have access to a printer at home, that's great. If you don't have access to a printer at home, then we might just need to fill these in on paper, which is fine too. All right. Natalie, I'm going to ask one more time kindly for you to focus on what's front and center.
Okay.
Pretty pleased with Tim Harris on top.
Yes.
All right.
Stop.
So we're hopefully familiar with, comfortable with the idea of work and the idea of power. Now, some of you who turned in calculations and conclusions last week, I did make comments, and it would be worth looking at those. You're always welcome to make corrections. But we're going to move on now with the idea of tools that we use to make work seem easier. So if anybody spent some time with Bill Nye on Friday, you were able to maybe start to get the idea of what a simple machine is. If anybody watched that, or if anybody just knows, can anybody name a simple machine?
Catapult.
Well, catapult is the combination of several simple machines.
Pulley.
Okay, so a pulley is an individual simple machine. Any others? Somebody's typing one.
A lever?
Yeah, a lever would be considered a simple machine. So these are really, really low-tech machines. Wedges, screws, inclined planes, wheels and axles.
A slingshot?
Slingshot would be, maybe it could fall under the category of lever. Let's transition into a definition of what it is. A lot of times I just open with the idea of naming simple machines, because a lot of times we tend to list things that are actually way more complex, like a catapult, pretty complex combination. Even a pair of scissors is more, it's more than one simple machine combined together. Simple machines are really simple. A simple machine is any device that makes work seem easier. And I say seem because we'll find out that they don't actually do more work for us. It's any device that makes work seem easier by changing the size or the direction of input force, or just force. So anybody that got that can read that back to us?
Any device makes work seem easier by changing the size or direction of input force.
Very good. Yep. And I can repeat the blanks if you'd like. Does anybody need me to repeat? All right, capital letter B is very closely related. We say that machines don't do more work. They do not do more work for us, they simply change force. So soon you'll start to hear me reference this idea of a force-distance trade-off. Simple machines are based on the premise of less force over a longer distance, a force-distance trade-off. Capital letter B one more time says machines don't do more work. They simply change force. Any questions on capital letter A or B so far? All right. I don't think I see any questions not being typed. So then we go to this demo. I used to do this demo in class where I had a crate full of bricks. And I asked somebody to lift the crate of bricks, probably in the neighborhood of 50 pounds, from the floor to the countertop. And I would just ask for the student doing that to be able to give like a qualitative response. In other words, just on a scale of 1 to 10, tell me how hard that was. And most oftentimes I would hear the students say something like, well, it wasn't that bad, but it did require quite a bit of force. So without the use of the simple machine, it requires a lot of force over over a short distance. So again, I just want to clarify what you're seeing here underneath lowercase letter A. This is the word lifting in the demo. Lifting a crate of bricks straight up to the countertop requires a lot of force over a short distance, so we get some work. I was a little perplexed by some of your formulas that you used in your calculations for a powerful workout. My guess is that we were maybe cruising the internet for those formulas. Don't do that. Use what we have in our toolbox. Work equals force times distance. Force in newtons, distance in meters. Then what I would do in the demo is assemble a simple ramp, an inclined plane, which is a simple machine. And it would be a couple of pieces of lumber, 2x4s, that were really long. And we would put the crate of bricks on the ramp, and we would drag the crate up the ramp to the countertop. And I would ask the student who demoed this the same question: how hard was that on a scale of 1 to 10? And invariably they would say, well, it didn't seem that bad in terms of force, less than lifting, but I had to do it over a longer distance. So we might find that the amount of work done, both lifting straight up and using the ramp, equals about the same. Lifting is lots of force over a short distance. Using the ramp is less force over a longer distance. What other force is involved when we use this ramp that's not present when we lift?
Friction.
Exactly. Who is that?
Noah.
Thank you, Noah. Yeah, we got to overcome friction. So there's some waste force involved when we have to overcome friction. So we'll wrap up our notes here with this idea that when we use a simple machine, less force makes the job seem easier. Eventually, if I keep adding bricks to the crate, it may not be a task I can accomplish with just lifting. So I have to employ the use of a simple machine like an inclined plane, where yes, we have a greater distance to overcome, but less force over that longer distance makes work seem easier. It's that force distance trade-off. And we'll get into Roman numeral 2 tomorrow. If you're done with all parts of a powerful workout, part 1, the calculations, the conclusions, you're done for today. If you're not done with 1 or 2 or all of those parts, stick around.
Thank you.
Thank you.
Thank you.
Thank
Thank you.
You're
Thank
welcome.
you.